Okay, the last part of Lecture 7 relates to the different states of matter, solid, liquid, and gas, and how intermolecular forces are related to the states of matter. It turns out really it's all a balance. Everything has kinetic energy, and everything has these attractive forces. And it's going to be the balance between their kinetic energy and the attractive forces that's going to determine whether it's solid, liquid, or gas at any point in time. So first of all, let's just be clear about the differences between these. I put at each table a syringe with a solid in it, syringe with a liquid in it, syringe with a gas in it. All right. Take a moment, try and squeeze them, and see if you can see a difference. Okay, so which of them can you actually compress? The gas. Can you compress a liquid? Not really. Can you compress a solid? Not really. So, one key difference is that this is compressible. Oops. Solid and liquid are not compressible. Solid and liquid are sometimes called the condensed phases. And the reason they're called condensed phases is they are dense. The particles are really close together. And there might be a slight difference in density between a solid and a liquid form of a given compound, but it's usually not a huge difference in density. Whereas the gas, the particles are very far apart. And in terms of how they move, and what makes a solid different from a liquid? Well, we'll use the terms, in solid, the motion is just vibration. The particles can move, but they essentially just move in place. Whereas in liquid and gas, you can have vibration and translation, which means moving from place to place. So I want you to have pictures in your head of what this looks like for each state of matter. So let's put those pictures there. I'm going to start with the element bromine, Br2. There's a molecule of bromine. Actually, could we turn the lights off? All right, there's a single molecule of bromine. And then here's solid bromine. One other thing that distinguishes solids from liquids is in a solid, generally the particles are going to be arranged, or in most solids, not all, but most of the time the particles are arranged in kind of a repeating pattern. So there's solid bromine. If I allow them to move, notice they wiggle, but they don't move out of their positions. If we look at liquid bromine, what's different is now there's no set arrangement. And those particles, they wiggle, but they also will move from place to place. They're not stuck in one place. And then in a gas, now notice they're much farther apart. And now they're clearly vibrating. There's also rotational motion that I'm ignoring. So they vibrate, they rotate, and they translate. They move throughout the container. We can look at the same thing for water. So ice, there's ice with the hydrogen bond shown. And if I let them move, they stay in place. They wiggle. In a liquid, let's show the hydrogen bonds again. In a liquid, what we'll see is they wiggle, but they also move from place to place, and hydrogen bonds break and form in different places. And in a gas, water vapor, same idea. They're far apart. They're moving from place to place. So that's what I want you to keep in mind whenever we talk about solids, liquids, and gases. Now, we want to relate this back to the intermolecular forces or interparticle forces, and I've kind of added covalent network bonding in here because that is another kind of solid, and so I wanted the list to be complete. But I do want to make it clear there's a big distinction between these first two, and these are going to be much, much stronger than the remaining. So these first two are bonds. These are types of bonding. And then the rest of these are intermolecular forces. So you got forces holding them together. Now, what would make something go from a solid to a liquid or a liquid to a gas? Well, the idea is they have kinetic energy. We remember this from the first unit of the year. In any sample of matter, you're going to have some molecules that are moving fast, some molecules that are moving slow, an average somewhere in the middle. And you may remember this Maxwell-Boltzmann distribution, where you have number of particles versus how much kinetic energy they have. So here's another model. I don't know what element they're showing here, but probably a noble gas, just single atoms. And it has a moving plot over here of each particle and its kinetic energy. And so we can see most of the particles have relatively low kinetic energy. There's some that have higher. There's this long tail over on the right. And if you look at the model, you can see some of them moving really quickly. Here. We can track one atom, and that'll allow us to see its kinetic energy is going to change over time, because sometimes it'll get bumped into by a faster moving particle and then it takes off. Sometimes it bumps into a slower moving particle and then it loses kinetic energy. But we have this distribution of kinetic energy there. We can look at the distribution of speeds. This is actually carbon tetrachloride. Oh no, this is chloroform, I think. But here's the distribution of speeds. Again, some that are moving really slowly, a peak, ones that are moving kind of with middle speed, and then you get over to the right and you see there's a tail where you have some moving a lot faster than others. So that Maxwell-Boltzmann distribution, hopefully you remember from the first week. And the way that changes is, as you raise the temperature, you essentially increase the tail to the right. You move the big part of the graph to the right. At lower temperatures, there's more of a bump to the left. Does that all look familiar? All right. So we have these three factors going on for any substance. The strength of the intermolecular attraction. So stronger intermolecular attractions are going to favor what states of matter? Solid. Because the stronger the forces of the attraction are, the harder it is for the molecules to break away from each other and become a gas, get really far apart. What about temperature? As you increase the amount of kinetic energy they have, what state of matter gets favored? Gas. Because now they have so much motion that their tendency is going to be to break away. And then there's a third factor, which is pressure. If you raise something to really high pressure, what are you most likely doing to the distance between particles? You're decreasing the distance. The higher the pressure, the more you're squeezing molecules together. So the more likely they're going to become one of those condensed phases, either liquid or gas. Okay, so higher pressure favors, liquid or solid. And let's just focus in for a second on temperature. Okay. We have this Maxwell-Boltzmann distribution, and it turns out, based on the strength of the intermolecular attraction, there's going to be a certain amount of energy. Remember this, this x-axis is kinetic energy. Based on the intermolecular attractions, there's going to be a certain amount of energy required to overcome them and for the molecules to undergo the phase change. So this energy that's required for phase change, this is based on the strength of the intermolecular attractions. If there were really weak attractions, where would I put that? Where would I set that energy needed for phase change? Would it be a large amount of energy or a small amount of energy? Small. So for weaker attractions, this line would move to the left. Whereas for stronger attraction, it's going to take more energy to overcome them. Now the key point that I want you to take away from this graphical representation is that there's always going to be some molecules in this tail on the right that have enough energy to undergo the phase change, have enough energy to break away from their intermolecular attractions. And that's going to be represented by everything under this tail. And what do you notice about the size of what I'm shading in based on temperature? At low temperature, is it most of the molecules that can undergo the phase change? No, at low temperature, it's just a tiny fraction. Whereas at high temperature, and as you raise the temperature and this graph shifts to the right, you get a greater and greater percentage of the molecules that can undergo the phase change. And so just to leave with a visual for the day, and then we'll pick this up. We got just a tiny bit more to do tomorrow. Here's my ice again. Remember, ice has these hydrogen bonds. It's in this very regular pattern. And if I turn on the simulation, molecules are stuck in place. They don't break the pattern. They just don't have enough kinetic energy because they're cold. But if I increase the temperature, what happens is now the majority of them have enough energy to break those intermolecular attractions. And so we go from a solid to a liquid. For the sake of the simulation, it had to raise the temperature by 200 Kelvin to make it happen because the time scale here, it's measuring on picoseconds, 10 to the negative 12 seconds. So if you want to actually be able to see it happen, you have to kind of give them lots of kinetic energy right away. But that's the idea with melting is you go from not enough energy to break away from the attractions to having enough energy to break away from the attractions. And we'll pick that up tomorrow.